Welcome to this explainer. Today, we're diving into the fleeting, totally invisible world of reactive intermediates. You can think of them as the ghosts of the molecular world. These are short-lived, transient structures that quietly dictate exactly how chemical reactions actually happen, and get this, sometimes they exist for literally just a fraction of a microsecond.
So, here's our roadmap for today. First, we'll be mapping the energy landscape. Then, we're going to look at the Hammond postulate, dive into carbocations, unravel the non-classical ion mystery, and finally wrap things up with carbanions, radicals, and carbenes.
All right, part 1, mapping the energy landscape, peaks and valleys. To really understand where these intermediates live, we first need to get a feel for the terrain of a chemical reaction. Think of the reaction coordinate as, well, basically a specific hiking trail that our molecules take over a massive mountain range. It's essentially a one-dimensional slice of a highly complex, multi-dimensional space, and it tracks the exact path a chemical system takes, going from a starting reactant all the way to a final product.
Now zooming out a bit, a 3D potential energy surface perfectly illustrates that whole terrain. It shows how molecules navigate through these deep valleys of stability just to overcome towering peaks of energy. As the atoms move around and bonds are breaking or forming, the energy of the whole system shifts. It's always seeking that path of least resistance right through this molecular mountain range.
So if we slice that 3D map down into a standard 2D graph, the transition states are those high mountain peaks, the absolute points of maximum energy. Meanwhile, our reactive intermediates act as temporary little resting stops right down in the shallow valleys between those peaks. Now, they don't stay there long at all, but they are actual, distinct molecular entities.
Moving on to part 2, the Hammond postulate, a chemical rule of thumb.
Now, you might be wondering, how do we actually know what a molecule looks like at the very top of that mountain peak if we can't just hit pause on the reaction? Well, the Hammond postulate gives us a totally powerful clue. When looking at reaction curves, this postulate basically states that if a transition state, so the peak, and an intermediate, the valley, occur consecutively and happen to be close in energy, then they're also going to be really close in structure.
The real crucial point here is that whatever features stabilize our temporary valley resting stop are also going to lower the height of the mountain peak we have to cross. Because their energy levels are so similar, their molecular structures only need a really tiny reorganization to interconvert. This is huge because it beautifully explains why certain chemical pathways, like forming a tertiary carbocation, happen so much faster and way easier than forming a primary one.
Okay, part 3, carbocations, positive stepping stones.
Let's officially meet our very first cast member living down in these valleys, the positively charged carbocation. These intermediates are honestly just incredibly fascinating. They carry a formal charge of +1 on a central carbon atom, and get this, they only have 6 valence electrons instead of the usual stable 8. Because of that, they are fiercely electron-hungry, and they actually adopt a totally flat planar shape. They essentially survive their super brief existence by leaning heavily on surrounding alkyl groups, which step up as these generous electron donors.
It's amazing how adding more carbon neighbors, like going from a lonely methyl cation all the way down to a 2-butyl cation, dramatically lowers the energy, heavily stabilizing the molecule. I mean, we're talking about a massive drop from 261 to 164 kilocalories per mole. By surrounding that positive charge with more carbon friends, you significantly stabilize these fleeting intermediates, mostly through effects like hyperconjugation. That brings us to part 4, the non-classical ion mystery. So this actually brings us to one of the most fiercely debated scientific mysteries in the entire history of organic chemistry. Literally for decades, chemists argued passionately over a very specific type of intermediate. The main question was, did it break the standard textbook rules of carbon bonding? Like, could a carbon atom really connect to more than just 3 atoms while resting down in these energy valleys? We're talking about comparing classical carbenium ions, which are trivalent, meaning the carbon bonds to exactly 3 atoms and sits perfectly flat, against the highly theoretical non-classical carbenium ions. In this non-classical state, carbon miraculously becomes hypercoordinate. It connects to more than 3 atoms, sometimes even 5. And it does this using entirely delocalized sigma bonds that are just shared right across multiple nuclei. Sounds a little crazy, right? When they applied this whole framework to a specific problem, the big question centered around a uniquely reacting molecule called the norbornyl cation. Was it actually just 2 classical ions rapidly flipping back and forth, kind of like a windshield wiper?
Or did it exist as one single, stable, bridged, non-classical ion?
Now think about that completely unique bridge structure. To finally solve this massive debate, researchers literally had to cool the reaction down to a staggering -150 degrees Celsius. By dropping the temperature that drastically, they were attempting to completely freeze the molecular microsecond. They wanted to stop any rapid shifting cold in its tracks so they could finally get a clear, undisputed look.
And you know what? It actually worked. By using NMR spectroscopy at that ultra-low temperature, the data definitively confirmed that the Norborn alkylion absolutely exists as a bridged, non-classical intermediate. That hypercoordinate carbon was totally real. It was a true scientific mystery, solved simply by freezing these elusive characters right in their tracks.
And finally, Part 5, Carbanions, Radicals, and Carbenes. Let's check out our final set of characters and see how their totally unique structures dictate their behavior. Take Carbanions, for example. These feature a carbon atom holding a negative charge. But here's the wild part. Their stability order completely flips depending entirely on their environment. If they're just floating freely in a gas phase without any solvent interference, bulky alkyl groups polarize electrons away from the charge, which makes a T-butyl carbanion the most stable. But if you drop them into an aqueous solution, all the complications of the solvent molecules flip the rules entirely. Suddenly, the methyl carbanion becomes the most stable.
Now, radicals play by slightly different rules. They possess a single unpaired electron, making them paramagnetic, meaning they're actually drawn to magnetic fields. Much like carbocations, they're stabilized by hyperconjugation, so a tertiary radical is highly favored. But unlike those perfectly flat carbocations we talked about earlier, radicals often prefer to sit in a slightly staggered formation. Bridgehead radicals, for instance, end up being significantly less strains than their positively charged counterparts. Finally, we have carbenes. These guys are completely neutral, but they are highly reactive intermediates. Depending on what groups are attached to them, they'll either pair their two non-bonding electrons tightly together to form a bent singlet geometry, sitting at a roughly 105-degree angle, or they'll unpair those electrons into a much wider triplet stance, spreading out to around 136 degrees. It's just this incredible structural dance, and it is dictated entirely by the surrounding substituents.
Understanding these invisible, short-lived characters is absolutely key to controlling chemical reactions. By knowing exactly what's going down in the valleys of that energy landscape, whether we're dealing with a flat classical cation, a bridged non-classical structure, a flipping carbanion, or a bent carbene, we actually gain the power to steer the reaction exactly where we want it to go. So, I'll leave you with this. What future molecules, life-saving medicines, or totally revolutionary materials could you build if you mastered the molecular microsecond?